Swayam Prabha. Digital India. Educated India.
Okay, I don't know how you have seen mass spectrometry, but we will summarize the whole aspect in starting from fundamentals to all the way up to structural characterization. Doing a justice in 2 minutes, all of this is going to be very challenging. Okay, we do it roughly about 10 hours of a time in the class. So in a semester, we use roughly about 10 hours for doing mass spectrometry. Okay. Yeah, remaining hours will go for UV, IR and NMR and all that. Okay. So 1/4 of the time will be invested on mass. What I would like to do is to give you a brief overview and then quickly get into structural elucidation using mass. Okay. Probably I will tell you about the key aspects of different sets of organic compounds, what you will look at in the mass spectrum, and how do you go about coming back and then realizing, oh, this is the compound that I have. Okay. So, overall, you know the terminology, I suppose. Why mass spectrometry? It is not called mass spectroscopy. Right? Why? It doesn't use? It does not use an electromagnetic radiation, but instead it is an ionizing beam. Okay. So, we call it as spectrometry instead of calling it as spectroscopy. That's the very first thing. And it's a very smallest scale. When you are talking about mass spectrometry, we are dealing with the very, very smallest scale. It is not because of the size of the mass spectrometer. Okay, I am saying this. It is just because the mass spectrometry or the mass spectrometer deals with molecules. Okay, molecules are a very tiny size, right? Usually, you will not be able to see them. So, it deals with the smallest scale in the world is what I have summarized as, right. Over the past decade, if you see, there are a lot of technological advancements. Initially, we were more worried about small molecules and then slightly medium-sized molecules. Now, the mass spectrometry could be very useful in terms of characterizing proteins, peptides, polymers, so on and so forth, right. Metallopolymers, metabolomics. In all the areas, you will see a lot of application in mass spectrometry. And various soft ionization processes that has been developed is a very key aspect in mass spectrometry, which has helped in an advanced level characterization. Otherwise, characterizing proteins and peptides is not going to be an easy task. Okay. So, these soft ionization techniques are developed, and this helped the mass spectrometry field to grow drastically. So, these are some introduction. The soft ionization techniques are nothing but electrospray ionization and matrix assisted laser desorption techniques and so on. Mainly in the biological areas, you see a lot of these applications coming up. Okay, so why mass? Again, various applications. Many bullet points are there as you may go through, right. Because of not only the structural elucidation, but also it helps in various other characterization. Mass spectrometry is also becoming important. One such example is solid state devices. All of us have mobiles in our hand, right, and also laptops. So, after a while you see the displays are going bad. Nowadays displays are composed of organic LEDs. Organic LEDs are nothing but thin layers of organic molecules, films, right. And when you subject to electricity, the light emission happens, and that is what we are using in devices. And all of this were built by organic molecules. So, with the time, sometimes your display may go bad. You will see with different colors coming up and causing problems, right. You are not able to see the actual color and so on. It's because of the decomposition of these organic molecules happening in these layers. If you want to know what kind of decomposition that has happened, maybe you may want to subject it to the mass spectrometry. What you need is a very tiny amount of sample, few nanograms, right, even picograms. You can inject it into the mass spectrometer and it will be able to tell you what are the decomposed segments that have come up upon electrical impulse. Okay. So, to begin with, you had a molecule, now it has decomposed and you know what you want to know from that. Okay. So, then you can develop a new molecule which can be stable and then again test it for LED applications and so on. Okay. So, the chemistry goes like this. So, for that proportion, you will, for that component, mass spectrometry is useful. Analysis of alkanes in blood, for example, people who are working in petrol bunks, they spend a lot of time, right, filling petrols for each one of us. And what happens is during the process, there in the blood, good amount of concentration of heptanes or these higher alkanes are present, and sometimes it will cause problems to the people who are working there. And you can take the blood sample, you can analyze, you know what kind of contamination that is present in the blood, particularly the alkanes that are, they are exposed to, which will come to know in. So, likewise, many other examples, explosives, adulterants, counterfeits, right, in sports and areas people use drug, and you can identify what kind of drug molecules that they have used. There are a lot of database available with respect to mass spectrometry, right, various mass spectrums are available. You can overlap quickly, you can find out what is the drug molecule that a spokesperson has used. With a database match, you can easily find out. Every company now develops this database and it's easy for you to find out. Few other examples, likewise you can list so many of them, and the slides are not enough. Okay. So, because of these applications, not only with respect to characterization of and structural elucidation of organic molecules, they are also useful in various other areas. Okay. So, that much you should know. Well, now we get into mass spectrometer. If you want to group the parts of the mass spectrometer, you will see these are the four main components. One is the sample inlet, right, which is usually at atmospheric pressure, or it could be at a slightly lower vacuum, okay, or reduced pressure than that of the atmosphere. And then you have ion source, mass analyzer and detector. All the three are enclosed into a very high vacuum chamber, very high vacuum, okay. So, this is a high vacuum zone, but the sample inlet and that portion, the sample inlet portion is usually of a slightly lower vacuum than this, okay, or it is at a atmospheric pressure. Now, in this case, if you are talking about samples, what type of samples you can use? You can use gaseous samples, you can use liquid samples, you can also use solid samples. Gaseous samples, no problem. In atmospheric pressure itself, they are gases. So, you can use them very easily, I would say. And if you are using liquid state samples, you may have to mix them with a solvent and then introduce it into this chamber. That liquid sample should volatilize and then that should be sent to the high vacuum zone, right. For volatilizing, maybe you need to reduce the pressure sufficient enough for it to volatilize, okay. That is one of the reasons why you keep this as a slightly lower pressure or atmospheric pressure. Atmospheric pressure means you can use gases or highly volatile, which the liquids that have very high vapor pressures, you can use it even at room temperature, atmospheric pressure, but which have, vapor pressures are quite low, and by applying vacuum you can make it as a vapor. Under those samples you have to provide it under slightly vacuum. Then you have sufficient vapors generated in this chamber. Now they will diffuse into the high vacuum zone because you have a vacuum gradient. One is at a lower vacuum, another is very high vacuum. So moment you inject the sample here, they would diffuse to the high vacuum zone, right? Because that's pulled into the high vacuum zone automatically. So sample insert is automatically happening in that cases. For example, solid samples, there is a thermal ionization zone. So there is a thermal zone. On top of it, you put the solid, sublime it by increasing the temperature, right? You can supply some voltage, your sample would sublime, and in the gaseous phase, they would enter into the high vacuum zone, right? So it leaks into the high vacuum zone, and all the samples, whichever I talked about, gas, liquid or solid, all three could be used for mass. Now, moment it enters into the ionization chamber, that's where you have ion sources which will do the ionization job, right? Ionization methods are different and ionization sources are different. So, depending on that, you will ionize. Ultimately, you will ionize the sample, right? So, when it is getting ionized, then these ions would fly all throughout the chamber, ionization chamber, and there are some mechanical tools or electrical tools which will push these ions in one direction, and all these ions fly in one direction in an organized way. Then it enters into the mass analyzer, which often is composed with the magnetic field, magnetic sector, and ions are deflected, right? Or whichever ions they are not deflecting, they are made to deflect by adjusting the magnetic field, and then all would reach the detector successfully at some point, and you will characterize whatever the ions that were present in your sample, okay. So these are the four main components that is very, very valuable in a mass spectrometer. Every component is important, whatever is shown here, okay. First step, as is mentioned here, vaporization of molecules into gaseous phase. For liquids, you have to volatilize, you have to make a vapor pressure, sufficient vapor pressure, and then let the sample into the high vacuum zone. With a solid, sublime, and then get into it. So what is mandatory is you have to vaporize the sample somehow. Second point is ionization of the molecules into positive or negative ions. When it gets to the ionization chamber, if it is a highly deficient compound, electron deficient compound, then when you are sending an ionizing beam, it would just catch it. It would hold with itself. In that case, it would become a negatively charged ion, right? If it is a highly electron rich molecule, you are sending in a ionization beam, which means high energy electrons, it would knock off an electron from the molecule because it is already electron rich, it is happy to donate. And that compound will now become a radical anion, radical cation, because it gives out an electron, it becomes a cation. In the case when it accepted an electron, it becomes radical anion. So you can generate either positive or negative ions, and the mass spectrometer detects these ions, be it positive or negative. In the detector mode, you have either positive mode detection, positive ion detection mode, or negative ion detection mode. You can switch the mode and you can find out the corresponding ions, okay, and you know which ion is coming out and so on. Third is the separation of ions, that is what is done by the mass analyzer. Depending on the mass by charge ratio, the deflection happens, right, and then you will send it to the detector, and magnetic field helps in that process. Okay, you can adjust the magnetic field, you can deflect all the ions that are generated here. Detection of ions is very important because many of the times what happens is, the moment the ionization happens, these ions wouldn't stay for a reasonable period. Within the short time it would die. Die in the sense, it would further fragment. So if the lifetime of these ions are very, very short, then that will not reach the detector. Before it reaches the detector, it would further fragment into smaller units. Then in the detector, you will not be able to detect those ions, but you will detect the fragmented ions. Okay, so this may happen also, and finally you will detect ions at the detector. Okay, So now let's go to the physical chemistry aspect of it. What happens? We said ionization happens, and ionization is often with a high energy electron beams, and high energy electron beams are often very high velocity, and electron volts are very huge. Okay, when that hits the sample, any organic molecule you can imagine, right? Every organic molecule would have some pi bonds, sigma bonds, you also have non-bonding electrons, right? All of this is there, and if something has to be, from somewhere an electron has to be removed, which would be the first part, either it is the non-bonded electrons or it is the pi or it is the sigma, from which one the ionization will happen faster, which is the location in the molecule where you expect the faster ionization. Pi, sigma or non-bonded electrons. Louder. Non-bonded electrons, good. So non-bonded electrons they are not bonded, right? They are observers, they are dictators, like we saw in the morning, right? So this non-bonded electrons are the first ones to get ionized. Second ones are then pi, third one is sigma. Okay, so that is the order. So if it gets ionized, ionization is very fast to process, and whenever you are talking about coming to pi and sigma and so on, the time frame for the electronic transition is few femtoseconds. When this high energy beam is hitting the molecule gets to the excited state, and randomization of energy happens, and all that happens after few femtoseconds. It gets to the excited state. From the excited state, within few femtoseconds, the energy is distributed all along the molecule, right? Whatever energy, ionization energy you supplied, and that energy is distributed all along the molecule. Now what is the next step? The energy that the molecule acquired is now distributed into all the bonds. So the energy is now located in the bonds, right? So in few picoseconds to few nanoseconds time scale, now vibrationally excited state, the molecule is kept in, right? So everything happens very fast. Just imagine the time scales, right? So every energy is now dissipated into the bonds. So every bond is kept to the higher vibrational excited state. Now from the higher vibrational excited state, the molecule should understand, hey, this bond is very weak. I am very weak. I am polarized. If I break, I can create a carbocation, stable carbocation, right? So it can decide. So the weaker part of the bond in the molecule is now going to fragment very soon. So fragmentation is dictated by certain rules, right? We will see that little later. So up to 10 to the power minus 6 seconds, that means if an ion that is generated in the chamber, if it can live up to 10 to the power minus 6 seconds, it will certainly reach the detector. If the lifetimes are shorter than few microseconds, then it will fragment within the ionization chamber itself. That means the ions will not reach the detector and you will not identify that particular ion. If you are not observing a particular ion in the mass spectrum, typically indicates that the lifetimes of those ions are very short. Short could be due to various other reasons. Could be structural reasons, mostly it is structural reasons, or it could be a highly volatile sample bombarded by high energy electrons, fragment further very quickly without hitting the detector. Okay, so this is the time frame you have to keep in mind. Moment the ionization beam hits the molecule, molecule gets to excited state in 10 to the power minus 15 seconds, femtoseconds. And in few picoseconds when it relaxes, molecule is placed in the higher energy vibrational excited state. And then it targets the bond, undergoes fission, and all these processes happen within few microseconds. Even after that it is stable, rock stable, it will reach the detector. If the lifetime is too short, it will cleave into fragments and then it will still reach the detector as fragment ions. Okay, this is the whole process that you have to keep in mind, which is the physical story behind this mass spectrometer function. Well, first part we have seen. So, how much should be a vacuum in the mass spectrometer? Vacuum is very, very, very low. If I have to tell 10 to the power minus 6 to 10 to the power minus 8 torr, very, very low pressure, and we don't want to keep very high pressure, otherwise you will promote collisions, right. So, if you keep very low vacuum, the collision between the ions is too less, right. That means what? You have to have a vacuum in such a way that the mean free path of these ions, right, should be as high as possible. It should not be in a closer proximity for these two ions to undergo collision within the chamber, right. So, that has to be met. And in a typical mass spectrometer length, if you see, it is 1 meter roughly, right. So, that means the mean free path of these two ions should be higher than 1 meter. That is a typical case, right. So, that is the way that the vacuum is managed within the mass spectrometer. And the ionization method refers to mechanism of ionization that is mostly defined by the substrate nature, right. But if you are talking about ionization source, it is the mechanical device that allows ionization to occur. So, ionization sources are different, and that is why we are having so many methods in mass spectrometer. ESI, electrospray ionization, MALDI, right, all of this is soft ionization, chemical ionization for example, all of this is coming based on the ionization method, right, sorry, ionization sources. Ionization methods are given here. How can you create an ion from a molecule? You can remove an electron from the molecule if you provide sufficient ionization energy, and you can create a cation, and in that case the mass spectrometer will give you information about the cation, right. What are the other ways to create ion? You can remove an electron by forming a cation, or you can add an electron to the molecule to generate an ion, right. When can you add an electron? If the molecule is highly electron deficient. It will naturally accept an electron to itself and you can generate an anion as it. So, you can detect anion, you can detect cation, you can generate them and you can detect them. Okay, what are the other ways? You can also protonate it, right. You can easily protonate the sample. Any hydrocarbon you take, you can treat it with very super acid, you can protonate, like arenes. Treat it with super acid, you can protonate, because you create a carbocation at the end. The carbocation is a cation you can generate, and it is a protonated form, so you can generate. You can easily detect that. Deprotonation can also be possible. Let us say you have acidic functionalities in the molecule. You have sulfonic acids, you have alcohols, you have carboxylic acids, so on and so forth, all acidic functionalities. You can easily deprotonate it. You can, before taking it to the machine, you can generate, right. In the laboratory, treat it with the base, deprotonate it, already have a anion, carboxylate ion or alkoxide ion, that you could put it in the mass spectrometer and then detect the anion as well, okay. So, you can do the deprotonation from a molecule which have acidic functionalities, and then you can use it for mass spectrometer. These are certain ways. You can also think of cationization. Like for example, you can form a sodium salt of the ion. You can also form an ammonium salt of the ion and then detect these cations using mass spectrometer. Okay, so there are various ways by which you can create ions either within the mass spectrometer or outside the mass spectrometer and then take it into the mass spectrometer. So, either of the ways is possible, right. So, you can create the ionization methods and use it. If it is a solution, you can transform it to a gas and then detect it, like we discussed earlier, right. If you can generate a sufficient vapor pressure, that will leak into the ionization chamber and you can get the mass down. So, any of these methods would be very, very useful. This is how a typical mass spectrum looks like, okay. Let us say your ions are reaching the detector, fragments ions are also reaching the detector, each one hits the detector, moment it hits it is going to create a signal and you plot them like this where x-axis is labeled as mass by charge ratio and the y-axis will have the relative abundance, okay. So, when you are looking at this mass spectrum, you will find the m by z in the y-axis. Usually for the charge ions that we have in an organic molecule in a mass spectrometer, charge is 1 usually, right. But there can be chances where you can get charge can be 2, say it is a dicationic nature, then you have 2 plus charge, then their mass will be divided by 2, okay. So, that you should be able to locate. See, in this mass spectrum, this is a compound of this, no, this is the mass spectrum of this compound. This is a dopamine. The molecular weight for this compound is given as molecular weight is 153, right. So, what do you expect in the mass spectrum for this compound? The molecular mass 153. At molecular mass or m by z value, charge is 1 assuming, right. You should get a peak at 153. Do you get a peak or not? There is a peak at 153 and that denotes the molecular ion peak. What is the molecular ion peak? The molecule as such has lost an electron, giving you a radical cation, and that cation has survived these vacuum conditions, high energy conditions, everything, and it successfully reached the detector. Now detector gives you a signal of 153 and you know that, hey, this is my compound's peak. Nothing is lost from my compound. The compound as a whole has appeared at peak 153. There is also a value that is 10 nearby, comma 10. This 10 corresponds to that of the relative abundance with respect to the y-axis, okay. Relative abundance in a sense that you also have other peaks there. With respect to the tallest one, how much it is, right. With respect to the tallest one, what is the tallest one here? Molecular mass of 124, that is the tallest peak here. That is assumed as 100%, that means you normalize it to 100%. With respect to that, relatively, how much is the height? That intensity is 10. So, it is 153, right. And if you are talking about peaks that are appearing at a lower masses, they are usually called as fragment ions. Fragment ions that are generated from this molecule. This molecule is now fragmented after the molecular ion generation, because it is a radical cation now in a higher energy state, it would further fragment and you have generated all these masses that are called as fragment ions. So, the m by z values at the lower masses correspond to fragment ions, right. And fortunately, the peak at 124 is the tallest peak and that is the most intense peak. So, you call that peak as a base peak, right. So, with the one which is tallest in the mass spectrum is often called as the base peak. So, molecular ion, can it be base peak or not at all? Can molecular ion be a base peak? No? All base peaks are not molecular ion peaks, but molecular ion peaks can be base peaks. Why? If the molecular ion is not fragmenting too much, right, it is a so stubborn molecule. It can withstand all the ionization energy. Obviously, it's not going to fragment. And whenever it creates a molecular ion, all of it reaches the detector within the time frame, and that is going to be of the tallest intensity. So you call that as a base. So you understand now, all base peaks are not molecular ion peaks, but molecular ion peaks can be base peaks, right? Since we have discussed this, now what you should understand is the relative intensities or the abundances of all the peaks that are shown there, it only denotes the chemistry of the fragmentation capabilities of these molecules, right? Some can fragment more than the other, and some ions can fly faster than the other, right? All these chemistries associated with the fragmentation, right? If you are seeing in the if the intensity of this is taller, means the chances of generating that particular unit fragment to generate that particular ion is higher. That is what it means, okay. So the shorter ones mean they also fragment but with less efficiency, right. So that is the chemistry of the fragmentation that you will see in terms of the relative abundance. Can you see peaks higher than the molecular ion peak? Yes, you can see. It could be because of the isotopes that are present in the compound. So those are isotope peaks. You can also have it as adducts, as we saw previously. You can have molecular ions combined with Na+, molecular ions combined with K+. You can also have molecular ions combined with right, some solvent molecules at times. You can also have combination with ammonium ions. So all of these adducts, for example, if you are doing chemical ionization, the gaseous chemical that they use can form an adduct with your molecular ion. So in mass spectrometry or in the mass spectrum, you can also see masses of higher value than your molecular ion. Okay, it depends on the technique that you are using, right. So you will also see dimers, adducts and the higher one. Lower abundance peaks are often fragments generated from the main molecule. Okay. So this is usually a bar diagram. It is not like NMR where you saw a peak. IR has a very relatively broader peak. UV has a very broad peak, right. So you cannot correlate with that. These are just histograms and you will be able to interpret. Fine. So look at the sources of ionization. There are so many sources that are known, right. Most of the textbook give you a brief introduction to all these techniques, but they would spend more time on electron impact ionization, right. We will also do the same, right. These are the other techniques, mostly they are dealing with soft ion techniques, right. You should know what they are, but in your exams they will be mostly focused on electron impact ionization, which is extensively used in chemistry, right. So what you will get from here is the molecular ions, or sometimes molecular ions can be absent also, because they would fragment to give other fragment ions very rapidly. Sometimes you may not detect them, but when you don't detect them, your life is going to be miserable. If luckily you are able to generate the molecular ion, then your characterization becomes relatively simpler, okay. So we will spend more time on electron impact ionization. This particular image, I think it is obtained from MSU, so credit goes to them. So what you see here is a simple setup of the electron impact ionization. This is the sample chamber. As we see here, the pressure is about 10 to the power minus 2 torr, right, and you can see the volatilized sample that is there in the gaseous phase. And here you look at the pressure is much lower than this, which is 10 to the power minus 7 torr. Moment you create the pressure gradient, this side pressure is higher than that of this side. So samples from that end will diffuse into the low pressure region or high vacuum region. When it leaks into this chamber, there is a filament here which supplies very high energy electron beam, right? And these electron beams are encountering the gaseous molecules that are entering into the chamber and then knocks off an electron from the compound. So ionization happens inside. After this zone ionization happens, you can see these are all charged molecules. They can be filling this ionization chamber, but with the help of repeller electrode, which is also positively charged, it will just push away all these ions, right, in one particular direction. And hence you form a nice line of these ions proceeding towards the detector. There is also a pair of plates which are called accelerating slits, which will further push these ions away with much higher voltage. Okay, they would repel this, they would just push these ions fastly and then reach the magnetic field. Because these are charged ions, moment they come to the magnetic sector, they would deflect, right, because charge under the magnetic field would deflect. And what you see is the deflected ion beam that is reaching the detector. Some of the ions that are much heavier, heavy ions would take a longer curvature. If it is a lighter ions, it would form a shorter curvature and they would also hit this. So you can adjust the magnetic field from 500 to 8000 Gauss, slowly adjust the magnetic field and bring these ionization beam to the straight path which can reach the detector to generate the mass spectrum. Okay. So if you look at this equation, which just equates the potential energy of the ion to the kinetic energy of the ion. Next is depending on the curvature. So the centrifugal force and the centripetal force, when it becomes equal, that is when the track of the ion is successful in reaching the detector. So if you just take these 1 and 2 equation and then do some shuffling, you find that m by z is equal to b squared r squared divided by 2b. What it means is the mass is directly proportional to r, inversely proportional to the voltage, and it is also directly proportional to the magnetic field. So you can, to change the radius of curvature r, you can use the accelerating voltage. You can also modify the magnetic field strength in such a way that these ions are successfully reaching the detector. Okay. When the ions are made successfully reach the detector, that is the time you will get a signal for that particular ion and you can use the mass spectrum to identify. Now the chemistry again behind what is happening into the electron impact ionization. Usually 70 electron volt worth ionization beam is hitting the sample, right? Why 70 electron volt? What is the typical ionization energy for any organic or inorganic molecule we are encountering? Their ionization energy of a typical organic molecule or inorganic molecule will not even cross 10 electron volts. Okay, let us say 14 electron volts also. Then it is sufficient for you to hit with the 14 electron volt ionization beam, right? You need to know the ionization energy of a compound. Moment you know the ionization energy of the compound, then you provide appropriate energy for it to undergo ionization. But why 17 electron? If you take any of the functional groups that is denoted here, H to methyl to olefin, then acetyl and so on, halogen, maximum it has reached is only 11.07. Let's even say 15 electron volt. But why to provide such a high energy beam for a molecule to undergo ionization? You need to lose one electron from the molecule. So for that, the ionization energy that is sufficient you can provide. But what we are providing is more than what is necessary. Because you are providing such very high energy, the molecule also undergoes fragmentation. Very high energy when you supply, right? So whatever molecule that takes up this energy, it has more than the energy that it has to undergo ionization. Okay, it ionized. After that also it has energy. What will it do? That's when the dissipation along the bonds happens, starts to break at different places, weaker places in the molecule. Right? So if that has to happen, if all this happens, why to provide 70 electron volts? Lifetime? What is that? Someone said lifetime. You want to say something? How is it correlated to lifetime? See, what basically happens is this, I'll show you. This is the picture, right? So first look at this, we are increasing the electron volt slowly. The compound under this study is benzoic acid. We have taken benzoic acid, molecular weight is how much? 121, right? So molecular weight is, here plus, so it's 122. So when you take benzoic acid, you have a molecular ion, only one peak. If my mass spectrum is like this, I'll be very happy. There's only one peak for my compound, so I know the molecular mass of this, so I know this is benzoic acid. Right? I can tell immediately. But life is not that simple. Here m dot plus. What happens if you increase the electron volt, ionization energy? You start to see one more peak, which is appearing at a lower mass, 105. What is 105? If you look at this, the loss of the OH radical, right, creating the benzoyl unit, that azylium ion is what you are seeing here, which is located at 105. Okay, you further increase the voltage to 15 electron volt, the intensity of this is increased, correct? That means what? More of this m dot plus is undergoing fragmentation now. More of this m dot plus is undergoing fragmentation to give you this particular ion, which is 105. Okay, further from 15 electron volts to 20 electron volts, you start to see one more fragment ion peak at a lower mass, m by z 77. That m by z 77 corresponds to none other than the loss of carbon monoxide gas to give you simple phenyl cation. Right? Doesn't stop here. Okay, if I go 30 electron volt, the molecule again is undergoing fragmentation. That means the phenyl cation also possesses excess energy with itself. Right? Now it has to undergo fragmentation. The way it undergoes fragmentation is by the loss of acetylene. So it loses acetylene, which is what the molecular weight of 26, and you get the final cyclobutadienyl cation, right, with the molecular mass of 51, and that is the fragment that you are seeing here. Along with that, you are also seeing 39, something has happened to cyclobutadienyl cation also, and you are getting this 39. Okay, if I increase further to 70 electron volt, what basically happens is, afterwards not much of a fragmentation, that is the same pattern that you are seeing as you used 30 electron volts. Now what do you understand from this? If you apply 9 electron volt for benzoic acid, if she uses, let us say, 12 electron volts for benzoic acid, you may use 20 electron volts for benzoic acid, right? And in other part of the world, someone uses 30 electron volts for benzoic acid. Now you want to study about benzoic acid, you want to understand what is benzoic acid, the mass spectrum of the benzoic acid. What you will see is 4 different mass spectrum for benzoic acid. Okay, this is getting complex, because for the same organic compound, whether I do or you do or someone does in other part of the world, all should be same. Only then I will be able to compare. So the maximum ionization energy at which the mass spectrum is constant, right? is 70 electron volt. Highest ionization energy is what is fixed all over the world. If someone uses, someone reports this compound in the literature based on electron impact ionization, they must use 70 electron volts. And in IIT Madras, if I am using and someone else using from other institute, electron impact ionization, everyone will follow 17 electron. So that the mass spectrum that you produce, I produce, from other country producers, everything will be same. So it is comparable. That is the reason why we keep extremely high energy ionization beam that is supplied for this one. That has become a standard all over the world. Okay. So now what happens? Okay, in EIMS, electron impact ionization, molecule is bombarded with high energy, and we know collision not only ionizes the molecule but results in absorption of considerable amount of extra energy by the molecule, right? And this extra energy places the molecule in a higher vibration energy state, like we discussed before. Bond breaking occurs from the vibrationally excited state. And all of this happens within a time frame of about few nano to microseconds. It is all done. Now the excess kinetic energy imparted on the molecule during EI process leads to extensive fragmentation of the molecular ion, because molecular ion still has excess energy after ionization. Right? Now what does it do with this energy? And you have put it in a very high vacuum. There's nothing much to do other than to ionize. And that's what it does. So you have fragmentation of organic molecules reproducible under standard ionization conditions. The standard ionization condition is 70 electron volts. Now some compounds fragment so easily that the lifetime of the molecular ion is too short to be detected in the molecular ion spectrum. Like we discussed, their lifetime is too short, less than few microseconds, and hence it undergoes fragmentation rapidly. You may not see the molecular ion in the mass spectrum, but you will see the corresponding fragment ions. High molecular weight compounds are relatively non-volatile, for example proteins or biopolymers such as proteins, or it could be polymers, for example. All of these are high molecular weight and you cannot bring it to the vapor phase, right? Because they have a very low vapor pressure. Even under very high vacuum, whatever we discussed, it is very difficult for you to bring it to the vapor phase, and hence these molecules are not very good to be subjected to EI mass. So you should know what kind of compounds to be put to what kind of mass spectrometry techniques. These are high molecular weight, so EIMS is not suitable. But what is suitable? ESI is suitable, MALDI mass is suitable, and these are the techniques where you can use high molecular weight samples. Coupled with fragmentation problem, it is also very difficult to analyze such high molecular weights because fragmentation could be everywhere, right? To talk about a big protein backbone, you put this in EIMS, let's say you just put it on a substrate, inject bombard it with EI, it would fragment everywhere. It is very difficult for you to identify which is connected, whether it is the N-terminal protein or C-terminal protein. All that becomes very, very difficult for you to identify. So it makes no sense to put it under EIMS. That's what is written here. If the molecular ion has a lifetime greater than 10 to the power minus 5 seconds, microseconds is what we said, then the molecular ion peak will appear in the MS. If it is less than that, it will not appear because it will be chopped in the ionization chamber itself. Not all molecular ions formed during ionization have the same lifetime. Some have shorter than the others. In a typical EIMS spectrum, corresponding to both molecular ion fragment ions are often seen. Usually you see both of them. Sometimes you may not see the molecular ion just because their lifetimes are too short. Okay. So fragmentation process is always a unimolecular process in the mass. That means you start from a molecule. After removing an electron from there, it produces a molecular ion. This molecular ion is supposed to break further. So it is always an unimolecular pathway. You generate a fragment, that fragment further generates, right? And further the smaller fragment undergoes further fragmentation, as we saw for the case of benzoic acid. So it is a unimolecular pathway usually. So it's easily identified. So this is a holistic scenario. You start with a neutral molecule, you bombard it with the high energy electron beam. That electron comes and hits the molecule. removes one more electron from the molecule and takes it along with itself. So, what you are creating in the process is one molecular ion plus two electrons. The one which is hitting the molecule and the one that is ejected from the molecule, right. So, you have two electrons coming out, right, and this is generated now, it has excess energy, so it will further cleave. If it is a radical cation, it can cleave into a radical cation and a neutral molecule, right. So, you have dot plus and you have created a neutral molecule. One more way to cleave the radical cation is to create a cation and a radical. So, this radical cation can cleave either to a radical cation and a neutral molecule, or the radical cation can cleave to a cation and a radical. So, these are the two pathways by which the molecule can undergo cleavage. Okay. To start with, A is a even electron species. Every organic molecule is an even electron species when they are neutral. If you remove an electron from there, it becomes odd electron species, right. So, if you are talking about this particular ion, radical cation, electron count is how much? Odd, because you have removed one electron from the even electron, right. Now, from the odd electron, you have generated a cation and a radical. So, what are you generating? Cation is, what is the number of electron? From an odd electron radical cation, you have now divided into two, one is a cation, another one is a radical. So, cation should be an even electron species and radical should be a odd electron species. You understand? But how about the molecular weight? To start with, let us say it is an even molecular weight compound. Now, if you are creating a radical cation, mass is odd or even? Electron count is odd, mass is odd or even? Nothing happens to the mass, same atoms are present, so it should be even, right. So, radical cation, electron count is odd but mass is even. Okay, if radical cation cleaves to a cation and a radical, so cation's mass is going to be even or odd? Cation's mass is odd, radical's mass is even. Okay, so you must have to take some examples, write down, and then you will figure out what it is all about. Okay, so you need to know the electron count, you should also know the mass nature of these systems. Of course, whatever we are talking about, this neutral giving you molecular ion, and we are saying that it is an odd electron species but with a even mass count, right. But if you are having nitrogens, then this rule will be completely different, right. Okay. So, molecular ions of organic compounds are always odd electron species, they are radical cations and anions. Odd electron ions have even mass if no nitrogen is present, and fragmented even electron ions have odd mass. The most probable fragmentation is the one that leaves the positive charge on a fragment with the lowest ionization potential. That means wherever the cleavage is happening, the resultant ion should be stable in some form, right. So, how can you understand that? There is something called Stevens rule, which talks about when you have small alkyl chain, long alkyl chain, it is fragmented against the long alkyl chain. If you have a bulky substituent there, you have a linear substituent there, the cleavage happens at the bulky substituent side, not at the linear one. Likewise, there are other factors that can come into picture, stability of ions. If you can create a benzyl cation which is stable, if you can create isopropyl cation, it is stable, right. If you are cleaving a tertiary-butyl cation, it is stable. So, the stability of those cations that you are resulting is also going to be dictating in terms of how it is going to fragment. And negativity, electronegativity is also an important thing, right, which decides the neighboring bond undergoing a fission. You call that as an alpha cleavage, homolytic fission. and that is decided by this electronegativity. Polarizability is another factor which can also help you in deciding where the carbon-carbon bond or carbon-X bond could undergo a cleavage. Resonance stabilization is another driving thing which can also help you in identifying where exactly the bond could cleave. Okay, and octet rule, of course, you would fulfill the octet rule, and that you have to keep in mind. What you can identify from the molecular ion in the mass spectrum? We'll first talk about only the molecular ion. So I don't know whether we'll have time to go. So only molecular ion alone, if you focus, there are too many things in the mass spectrum you can infer, right? Molecular ions, as we said, are odd electron species, but molecular weight wise it is even, right? So if it is it's an odd electron species, so this is often the highest mass in the mass spectrum. As long as you are able to see the molecular ion peak, it is good. You can come back and understand the fragment ions and then propose the structure. If molecular ion is lost, you are not seeing it, or with a very low intensity, then you are into a big trouble. Low intensity is still fine, but if you don't see at all, then it is you are in a big trouble. You don't know how the fragment ion, how you will attribute to the meaningful structure. That is not possible. So next is the nitrogen rule, and you know whether the compound has nitrogen or not just by looking at the molecular ion peak in the mass spectrum. If odd number of nitrogens are present, 1 number of nitrogen, 3 nitrogens are present in your compound, 5 nitrogens are present in your compound, then the molecular mass of that particular compound, m dot plus peak, that's going to be odd. Okay? If there is even number of nitrogens in a compound, or there are no nitrogens in the compound, in both the cases the molecular ions are going to be even. Okay? So if you have the molecular ion which is odd, then immediately it should tell you, hey, my compound has 1 nitrogen, man, or maybe odd number of nitrogens. You can tell that. Immediately you can tell. You should not even think about it for too long. If the molecular ion peak is even, that's when you have confusion, because you don't know whether there are even number of nitrogens or there are no nitrogens. So you can propose a molecular formula with even nitrogen. You can also propose a molecular formula with no nitrogen. But how do you know which one is correct, which one is not correct? That is where the high resolution mass spectrum is going to help you, right? So for example, here this is an ethylamine, right? It has only 1 nitrogen. Just to look at the chemical formula, C2H7N, molecular weight is 45, which is an odd mass. So the rule, nitrogen rule obeys here. You have 1 nitrogen, odd mass, so you are matching with that. Okay, what happens if you have diethylamine, right? Not diethylamine, sorry, ethylene diamine. If you have ethylene diamine, see the molecular weight is 60, even mass. So it can be 2 nitrogens, and that is matching, or no nitrogens. Here is a specific example we have taken to show that even number of nitrogens are giving you even mass. Okay, so keep that in mind. And so by looking at the molecular ion alone, you can immediately come to a conclusion about the number of nitrogens. Fine. Next is the precision mass. Precision mass gives you a lot more information about the correct molecular formula of a compound. You must have added the atomic weights, combine atomic weights, and then arrive at the molecular mass. That's what you usually do, correct? You take the atomic weights, combine all of them in a formula, and then arrive at the molecular weight. Now this precision mass is not about summing up of just their individual atomic weights. It talks about how much each atoms weigh in a molecule. Weigh means weight. Weight of every atom in a molecule. Sum of all the weights of the atoms, and ultimately you calculate how much is the weight of this molecule. Okay. So there is a difference between the atomic weight and the absolute mass of an atom, accurate mass of an atom. Why is this happening? Because of the nuclear packing fraction. You have the nucleus and it has the role to play to the surrounding environment, keeps it tight, right? So the nuclear packing fractions induces the small mass difference, which is very tiny. And that very tiny difference is going to help us in a very big way, right? It is so accurate. Assuming carbon's scale as 12, this is the accurate masses of every atom. Precise mass you may call, right? Each atom, how much it weighs. If you calculate for hydrogen, it's 1.00785252, so on and so forth, many numbers after that, right? Similarly, for all of this, assuming carbon as 12, normalize carbon as 12 because it's the most abundant element. Carbon is most abundant element. If you set that to 12, then remaining things will fall in line. So assuming this is 12, you calculate the accurate masses of all of this. In what way it is helpful for us? If you look at this formula, let us take formic acid and dimethyl ether. What is the molecular formula for both, a molecular mass for both of this? For formic acid it is 46.0054, dimethyl ether is 46.0340. If you would have taken only the atomic weights and then summed it, for both the compounds it will be only 46. Then you don't know what is the compound you have, whether it is dimethyl ether or formic acid, how do you conclude? Okay. But if you get 46.034012 so on and so forth, right, and you can confidently tell that, hey, look, my compound is only dimethyl ether, not formic acid here, right, you can tell that because it's so accurate, you can just match with the molecular formula, and that is the benefit of high resolution mass. Okay. And here are some examples. If you talk about this particular three set, nitrogen, carbon monoxide and ethylene, just sum the atomic weights, you get a molecular weight of 28 for all the three. But how do you know which is what? Just by doing a precision mass calculation. Nowadays, every mass spectrometer has this option. Every mass spectrometer has this high resolution mass spectrometer. If you are looking at, just ask them for high resolution mass, it will give you up to 5th decimal or 6th decimal point. So no one can deny that your molecule is your molecule. If it is deviating from the calculation, yes, they may say. But if it is matching this much level, no one can deny that your compound is not correct. Okay. So you look at here, for the precision molecular weight for nitrogen, it is 28.006148, carbon monoxide 27.99 only, right? And for ethylene, if you take, it is 28.03. So if you are getting up to this 4th decimal, you can certainly match it with ethylene, and if your compound is really ethylene. That is the benefit. Here is another set whose molecular formula is only given here. And you can see they have different elements, carbon and hydrogen and oxygen, carbon and hydrogen and 2 nitrogens. Mass is even. No nitrogen is also even. As you can see, 84, 84, 84. How do you know whether compound has nitrogen or no nitrogen and so on? If you are recording the high resolution mass, you know if you have 2 nitrogens, this should be the mass, 84.0688. If you are getting up to that much level, and you can be confident that my compound has 2 nitrogens. Okay, so that is the benefit of high resolution mass. So using the precise mass for each element, for each formula, mass differences appear in the 2nd and 3rd decimal places only, and then it becomes distinguishable. So you can go up to the resolution of 3rd decimal, 4th decimal match. Nowadays every journals are asking for your molecular mass is matching up to 3rd decimal, 0.003, 0.002 difference is only allowed. Beyond that, no, we don't consider. Okay, so that purity comes, elemental purity. Also it talks about not only the molecular weight. It also talks about the elemental purity, the composition of atoms or elements in the molecular formula, right? As we have seen here, no nitrogen, no nitrogen, nitrogen. So if you have two nitrogens, it can tell. So this is the advantage of precision mass. Now you are now focusing the direction to isotopics. By looking at the molecular ions, there are higher masses of lower intensity, higher m by z peaks, higher than the molecular ion, okay? But you have peaks of lower intensity. By looking at them very carefully, you can in principle arrive at the molecular formula, correct molecular formula. So the molecular ion region, you will get a set of isotopic peaks, and if you look at very carefully and then go back and calculate, you can know the molecular formula very accurately. Okay. So this particular mass spectrum has a molecular ion peak at 28. The compound that is used for this purpose is ethylene. What is the formula? C2H4, right? 2 carbons, 12 plus 12, 24 plus 4 hydrogens, 28. And you see a molecular ion peak at 28 with a maximum abundance of 100. So this is the molecular ion peak, is the base peak here. Now you can correlate, right? So this is this. There is also a peak at m plus 1, which corresponds to the m by z value of 29, right? So with intensity of less than 2, maybe less than 2 or 3, that much only. And there is also another peak. Are you able to see? No. I am also not able to see. But there is supposed to be a peak at m plus 2 whose mass is 30. Right? And that is quite negligible in intensity. Very, 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 very low. Maybe very close to the x-axis. Right? Very difficult to identify. Now what are these due to? You need to understand. Right? The peak that you are getting at 28 must have come from the most common or abundant isotopes, which is carbon 12 and hydrogen 1, right? And if you are talking about carbon 12 and hydrogen 1, if you sum their atomic masses, sum it up, molecular weight can come to 28. That is the molecular ion. Why should you see a peak at 29? Isotope peak. It could be, there is the, because of the 2 carbons, 1 carbon could be 13C. 1 hydrogen could be H2. But how much of 13C could be there? In nature, how much 13C abundant? Only that much you will have. What is the abundance of 13C? 1.1% or something. Right? So their intensity is now 1.1% roughly, to that level only. Right? So the intensity is close to 2.2, that is the thing that is coming up there. Not only corresponding to carbon 13, corresponding to the portion coming from H2 also. So you have to add these two to get to this number. Okay. Now what is the peak that you are getting at 30? There can be few molecules where you have carbon 13 also, along with H2 also. H3 is also can be possible, but its abundance is even more lower. Its abundance is even more lower, which is completely negligible. Okay. So that is observed. Even with this itself, we are not able to see the third peak, m plus 2, we are not able to see. And if you are going for 0.00001 and so on, completely negligible. You may not be able to see. So it is not worthwhile spending time in identifying every isotope, but what you should keep in mind is the observed isotopic peaks or observable isotopic peaks, you should be able to capture them. Okay. Let us say if you have an element whose isotopes abundance is quite bigger than 13C or H2, then what do you expect? The isotope signals of them, isotope peaks of them should be high, much higher in intensity. Correct? And you should be able to detect them without any difficulty. You don't need to zoom it and then find out whether it is 2.23 or 1.1 something and so on. So it is possible and you can easily detect. So examining the relative intensities of the peaks due to the molecular ion and the related ions that bear one or more heavy isotopes is another method of determining the molecular formula. So if you are seeing this kind of a composition of this much intensity, you can certainly say I have only carbon, I have only hydrogen. You can come up with that composition easily, right? Well, this is the list of abundance that you have. So 1H, 2H abundance is here, carbon 12 is 98.9 and carbon 13 is 1.1 percentage. The ones that are 100% abundance you have to pay attention. These are fluorines, phosphorus and iodine. All the three atoms having isotopes are natural 100% abundance. You should also pay attention to silicon and sulfur whose abundances of the isotopes are relatively significant. They are good, right? So when compared to hydrogen 0.015, carbon 1.1%, look at silicon which has an isotope which for 28 it is 29 is another isotope whose abundance is quite high. 30 is also quite high here, 3%, 4%. So the intensity should be much bigger than the 13C you saw before. Correct, no? If your compound has sulfur, again pay attention to the isotope for S32, there is an isotope of 34 whose relative abundance is also 4.22, right? With a mass difference of 2, M plus 2 with a relative intensity of about 4%, that means a compound may have a sulfur. So the relative intensities of the isotope peaks in the molecular ion region will give you a clear picture of what kind of elements you have, how their compositions are, how many number of such atoms are present and so on and so forth. Okay. So it is a typical table how you can use the relative intensities to distinguish the molecular formula also. So this is carbon monoxide, nitrogen, again the same example with a molecular mass of 28, right? Same mass, but initially we said we should use high resolution mass to distinguish them. You remember? So you have to use high resolution mass spectrometry, record the precision mass and that will help you to distinguish these two though the molecular weight is same. Now we are saying you look at the relative intensities of the isotope peaks. That should also tell you what is the correct molecular formula of your compound. Okay. So let us take carbon monoxide. The relative intensity is M peak is at 100% abundance, and if you take M plus 1 it is 1.12 relative intensity, and if you are talking about M plus 2 it is 0.2. If you are taking another molecule whose molecular weight is same, which is nitrogen here, M is 100%, M plus 1 is 0.76. What happens to M plus 2? It is not at all there, it doesn't exist. So by looking at that region, zoom it, right? You see only two peaks, you can attribute it to nitrogen. If you have three peaks with the relative intensities of this much in the y-axis, you can identify that this is carbon monoxide. You understand? So the relative intensities of the isotope peaks can be very informative in deciding the molecular formula. Another three examples that we saw before, ethylene, propane, and then you have diazomethane. Look at the molecule, this corresponds to here anyway. Okay, so this 2 corresponds to molecular mass of 42. If you compare the relative intensities of them, for C3H6 it is 100, M plus 1 is 3.34, M plus 2 is 0.05, whereas for diazomethane it is 100, M plus 1 is 1.87 and 0.01. So by just comparing the M plus 1 peak and the M plus 2 peak, you can conclude what is the correct structure you have. You understand? So this is the way to use the isotope ratios of the M plus 2, M plus 3 or M plus 2, M plus 4, whatever, you should be able to identify the right molecular. So the formula is, before going to this mass spectrometer, you can also put it into this equation based on the number of carbons, hydrogens, other elements that are present, and you know roughly what is the relative intensities of M plus 1, M plus 2 and so on. So you can calculate beforehand and then go to the mass spectrometer, sit and analyze, see, look at the relative intensities if the formula matches up. Okay, so this is possible also. And very importantly, what you should not miss is the halogen isotopes. Very, very important because they are quite abundant. Okay, if you talk about chlorine, it has two isotopes, Cl35 and Cl37 in a ratio of 3:1. Right, they have a relative ratio of 3:1. That means 35 is 75% in nature, and 37 is 25% in nature. So one is 75, another one is 25%, is quite significant. Not like carbon 12 and carbon 13. Okay, so if your compound has chlorine or bromine, their isotope peak should be very strong. You should be easily be able to observe them. Okay, and bromine has two isotopes, bromine 79 and bromine 81. Both the isotopes are of relatively same abundance, they are equal abundance. So one is actually 51 and another one is 49, so you can roughly consider it as 50-50. So you have a relative ratio of 1:1 abundance. So if a compound has one bromine, how many peaks you will see in the mass spectrum in the molecular ion region? You must see 2 peaks. What are they? No. 79 is for bromine. I am talking about the molecular ion. Let's say a compound M has one bromine atom. In the molecular ion region, how many peaks will you see? M and M plus, why M plus 1? Why M plus 1? The isotopes are separated by a mass of how much? 79 and 81. What is the difference? 2. Right? So when you are seeing the mass spectrum, because isotopes have a mass difference of 2, the molecular ion should also be separated by a mass unit of 2, because one molecule has 79, another molecule has 81. Correct, no? So the mass should be separated by M and M plus 2, but how many peaks will you see? 2 peaks will you see. Both of them are of same intensity because their abundance is same. 1:1 ratio. If it is a chlorine, one chlorine present in an organic compound whose molecular weight assume as M. Now how many peaks will you see in the molecular ion region? 2 peaks. How many peaks will you see? 2 peaks. What is the mass difference between them? M and M plus 2, so 2 mass units between them. What is the relative intensities of the 2 peaks? 3:1. Because that is the relative ratios of their abundance, and that should be replicated in the mass spectrum. So you will see 2 peaks, one is taller like this, another one is 1/3 of this. 2 peaks you will see, right, with the mass difference of 2. You understand? So because for the 13C and 1H, 2H, we saw 3 peaks, M, M plus 1, M plus 2. Why? Because their mass is differed by 1. First in the case 113C was present, remaining are all 12 carbons and 1 hydrogens. So mass difference is 1. Another case we considered, instead of all 1H, we considered 2H only. Carbons are 12 only. So again mass difference is 1. That is why we said M, M plus 1. We also considered M plus 2, where carbon can be 12. Sorry, one carbon can be 13. Another hydrogen also is 2. So now the net mass difference is 2. That's why M, M plus 1, M plus 2. Right? Here the mass difference between the isotopes itself is 79 and 81 in the case of bromine. Another case 35 and 37 for chlorine. So net mass difference is 2. Okay. So this is about it, and now this is the combination. Sir, how do I know? There can be one bromine, one chlorine, there can be 2 chlorines, there can be 2 bromines, 1 chlorines, there can be 2 chlorines, 1 bromine. All these combinations, then how do I know? Right? So this is the summary of this whole slide that which comprises of various combinations. It is not limited to only this, but you have various other combinations as well. So let's pay attention to the bromine. One bromine, when you see, the relative intensities are 100 and 98, that means roughly 1:1, I would say 50-50, right? This is 100 means you can also assume this to 100 with a relative ratio of 1:1 with a mass difference of 2, m plus 2. So in mass spectrum looks like this, m plus 2, 2 peaks. Let us say if the molecular weight for this compound is 120, then you will see a molecular ion peak at 120. You will also see another peak at 122. You understand? So that is the one. If you have two bromine atoms, one bromine can be 79, another bromine can be 79. One bromine can be 79, another bromine can be 81. Right? Both can be 81. So what is the net mass difference? 79 is natural. Let's say it is m. 79 and 81, m plus 2. 81 and 81, m plus 4. Right? So m plus 2, m plus 4 are 3 peaks you will see in the molecular ion region, with m plus 2 being taller, twice as intense as that of the m and m plus 4. Because we are concluding 79 and 81 and 79 and 81. Right? 79, 81 and 79 and 81. So both the possibilities combined together. So m plus 2 will have two possibilities and their relative abundance is top. Okay, you can also calculate this using a simple formula. You all may be knowing it. Do you know that or not? Are you guys aware about the formula? Let's say you have bromine you are considering, there are two bromine atoms. If you want to arrive at what is the relative intensity, so you can use this formula. So relative intensity ratio is 1:1, right? So let's say 1 plus 1 whole square. So A plus B whole square formula. So now what is the formula for this? A squared plus 2AB plus B squared. So 1 squared is 1, 2AB is 2, and B squared is again 1. So 1:2, 2:1 is the relative ratio. You want to try this for chlorine? Okay, so relative ratio is how much? For 35 and 37, 3:1. So do the same formula. 9:6:1. Do you see that or not? You have two chlorine atoms, 9:6:1. Okay, so this is the way you can calculate. You can do that for various combinations also. But there are two halogen atoms combined together, the formula would change a little bit. That is shown here. Let's say you have two bromine and one chlorine, because they have two different abundances, right? So you may have to say A plus B whole squared into C plus D, where C and D stands for the abundances of chlorine, which is 3:1 relative ratio, and A, B stands for the 1:1 relative ratios of bromine, right? Because your compound has two bromine and one chlorine, right? Under that condition, so this is the expanded form of that. If you put in this abundance into this and then arrive at the formula, you find that 7:3:7:5:1 is the ratio, and that is the ratio you will see here also. It's a 2 bromine and 1 chlorine, 3:7:5:1 is the ratio, right? And the mass spectrum will have a situation such as here, as you are seeing m plus 2, m plus 4 and m plus 6, because both bromine and chlorine has a mass difference of, and isotopes will have mass difference of 2, right? So the 2 difference is established in every masses. You have m plus 2, m plus 4 and m plus 6. That's fine. So molecular ion peak can give you a valuable information about all these set. Initially we said about number of nitrogens it can give, then you can use precision mass to come back and then calculate the molecular formula. You can also use the relative intensities of the isotope peaks and then come to the molecular formula. If the relative intensities are significant, keep in mind you should be worried about chlorine's presence, bromine's presence, or maybe sulfur or silicon, right? Any of these atoms could be present. and you can go back and calculate the molecular formula, right? So this is one of the aspects that you can rely upon. Now we go to fragmentation. We have only 30 minutes. We'll have to really hurry up. So fragmentation is the next part. Molecular ion is over. Now we'll worry about the lower m by z masses. Right? A molecule, when it is put under ionization, what are the ways by which it can fragment? If you look at that, so you start with even electron species. All organic molecules are even electron species, right? Now upon ionization, you create radical cation. One electron is lost, so you generate an odd electron species, right? So if you are starting from a radical cation, we said there are two pathways. Radical cation can fragment to give a radical cation or a neutral molecule, or it can cleave to a cation and a radical. These are the two pathways we mentioned. That is what is summarized here. You have an odd electron with a molecular ion, let us say. If it can undergo a cleavage, you can create a cation, even electron cation and a radical. If you are talking about odd electron radical cation, it can cleave to a radical cation and a neutral molecule. If it is a even electron cation, it just goes to even electron cation and a neutral molecule. Okay, so this is the combination, but from a cation you cannot generate a radical cation. That is not possible. So what is allowed is only these three processes. Along these processes, if it is fragmentation is happening, it is a favored process. The last one is disfavored. It is not allowed. Okay. So let's talk about the first mode of fragmentation. The common pathway by which fragmentation occurs is one bond cleavage path. There is only one bond cleaved at a time. Okay. When I say this, then something may be running in your mind. Then multi-bonds are possible. Huh? Is it really okay? Yes, multi-bonds are also possible. Two bonds can cleave at a time as well. For example, a scenario which you are talking about, retro-Diels-Alder reaction. Diels-Alder reaction forms with two bonds, and if it is cleaving, it also cleaves in the same way. So it is a retro-Diels-Alder, two bonds cleavage can happen. So under what conditions it can have, what should be the substrate then? It should be a typical cyclohexene type of a molecule, right? Cyclohexenes could be constructed from 1,3-butadiene and ethylene. Diels-Alder reactions between them could give you a cyclohexene. So if you put the cyclohexene or cyclohexene derivatives into the mass spectrometer, it can also cleave in a retro-Diels-Alder fashion, breaking two bonds. Let me come to that little later. But I worry about only one bond cleavage pathway. So let's start with benzyl bromide, right? So some details are given here for your extra information. It has one bromine. So you must expect two peaks in the molecular ion region. One is M, another one is M plus 2. So if the mass is 170, you should also see a M plus 2 peak which is at 172. Right? So what is the electron count? Because it is a molecular ion, it is odd electron, but mass is even only. Nothing has happened to the mass because it has not lost any atom. It has only lost an electron. Right? So if this has to cleave, where would it cleave? Br should be cleaved first. If that is cleaving, then you can generate a benzyl cation. Benzyl cation is very, very, very stable. Right? So how this cleavage happens, in a stereoelectronic fashion that we discussed in the morning. You can visualize how this fragmentation can happen. The CBr bond, right, with the CH2, this is a phenyl ring, let us say, okay, this is a phenyl ring, and there is a CH2, and the Br is like this. Anti-biplanar, where is anti-biplanar here? The phenyl rings, p orbitals are perpendicular to the plane, right, CH2, and the Br is sitting here. Now the CBr bond has a filled bond overlap with the vacant p orbitals on the benzene ring. Right? So it is a filled filled sigma to the pi. That overlap is there, that sharing is there, and hence this bond is weakened. CBr bond is weakened. Okay. So it is again, that is over. It is the only way by which ionization happens. When CBr comes in alignment with the p orbitals of the benzene ring, then that's when the electron density is drained to this, and this becomes weak and it becomes fragmented. And that this bond keeps rotating. CBr keeps rotating, and whenever it comes in alignment with the p, that is draining out the electron density and then pushes the Br away, like Br minus, right? So here there is a similar way it cleaves and creates a benzyl cation and then the Br dot. Now the benzyl cation is stable, so you will detect it in the mass, and this doesn't stay like this, that also you may know. It will undergo a rearrangement to give you a tropylium cation. Tropylium cation is aromatic, right? So every molecule strives for their stability, right? So they quickly undergo rearrangement, creates a tropylium cation which is aromatic, and that could be detected in the mass spectrum. So its M by Z is 91. So this is a cation, it could be an even electron species with an odd mass, and you have Br dot. Gone. Br dot is not detected in the mass spectrum because it is not an ion. It is like a neutral molecule. So mass spectrometer detects only the cation, giving you a peak at M by Z 91, sorry. So here is another molecule which is tertiary-butyl benzene, right? This is a tertiary-butyl benzene. Molecular weight is 134 and the molecular ion also has the same mass, 134. Now if this has to undergo ionization, what are the ways you can think of ionization? You can break between the phenyl and the tertiary-butyl carbon, right? Another way to break is to break the methyl, form the methyl radical and create a benzyl cation. Formation of phenyl cation is stable or formation of benzyl cation is stable? So formation of benzyl cation is stable, and that is the way it cleaves also. Usually whenever you have an alkyl chain attached to a ring or a molecule, it always thinks of cleaving a larger alkyl. Okay. So in this case, a last small methyl radical keeping the large alkyl unit, which is benzyl cation, and this is what you see at a M by Z value of 119, which you can detect. So it's all based on one bond cleavage process, right? And if you are looking at nitrogen compounds, how it may cleave? Again, one bond cleavage processes. So one nitrogen containing compound, you can look at the mass is odd, M by Z is 45, and if it is ionized, it is a radical cation, molecular ion is formed, and loss of the methyl radical, it is called as an alpha cleavage. The cation is, radical cation is here, so if it has to cleave, you can do a homolytic fission, move these bond pairs with fish hook arrows, right, on either sides, and one electron from this bond comes here, so this electron and that electron combines to gives you the iminium ion, right, and methyl radical is lost on the others. This again has a nitrogen, right, so but it has lost the other radical. Now you can look at the cation here is generating a even mass and an even electron species also, and with a mass of M by Z. Unlike the other case, where you have, when you had generated a cation, the mass was, when you had generated the cation, sorry, the electron was, if you had generated the cation, the mass was odd, right. Here in the nitrogen case, when you generated a cation, the mass was even, because you started off with the odd mass, one nitrogen, right. So you started with an odd mass. Now let us say here you can think of a hydrogen being lost from here, the adjacent one, not this bond but the CH, that is also alpha cleavage only. Instead of the CC bond, you can also cleave the CH here. If you cleave that, then again one electron comes here, so have the iminium form with the methyl with the mass of M by Z 44. losing the H dot hydrogen atom. Okay. So you can have two different possibilities, and these two masses you must look in the mass spectrum. Certainly you must be having the masses of these two. Okay, so this is all by one bond cleavage. We will go to the two bond cleavage simultaneous. So you are thinking of a retro Diels-Alder for this. If you are starting off with a cyclohexene radical cation, that means what? This literally represents that you have a cation here and then a radical here, or there could be a cation here, there could be a radical there. Right? So you can write the structure like that. That's why it is put in brackets and you have a cation radical there. Right? Because if at all you have to ionize this from the pi bond, you must have lost an electron. Correct? Because there is no non-bonded electron pairs there. Next one is the pi bond. So pi bond, from pi bond it must have lost an electron. So what you will have is the one side cation, one carbon carrying cation, another carbon carrying a radical. Now this one can undergo two bond cleavage process to give you a diene and a olefin. Okay. Similarly, like the retro Diels-Alder way, it opens to give you a diene and a olefin. So radical cation gives a radical cation here. The two bond cleavage process, you are starting with the radical cation, generating a radical cation along with the neutral molecule. This kind of neutral molecules are quite thermodynamically stable molecules. They are all stable molecules. You can lose ethylene, you can lose carbon monoxide, you can lose HCl, you can lose HBr. All that can happen via two bond cleavage process. Okay. So that is a common trend that you will see in these cases. Unlike the scenario that you saw before. In the previous case, what did you see? You started from a radical cation, but you are generating a radical cation and then a neutral molecule, or most often you are seeing a cation and a radical. That was the scenario we saw before, right? And here you are seeing a radical cation, that means you must be accompanying a neutral molecule, and these neutral molecules are usually thermodynamically stable molecules that are generated. Okay. So the bottom example, this is called a McLafferty rearrangement. You all must have studied it, right? Certainly there will be a question on this in some exam, I don't know. Always they ask questions on McLafferty rearrangement. So this particular, this is what? This is a ketone, right? Methyl propyl ketone, and you take this compound, ionize it, it has an oxygen, so non-bonded electron pairs are there. That is the one that will first get ionized, so you have a radical cation generated at the oxygen center. Now this radical cation, and because you have alpha, beta, gamma position, this gamma hydrogen could be abstracted through this carbonyl oxygen. Similar reaction you must have come across in photochemistry also. Do you study photochemistry? Norris type 2 reactions. Norris type 2 reactions follow the same rule as well. Gamma hydrogen abstraction to give you cyclobutanol is the structure that you would get if it closes. If it cleaves again, you will get a stable alkene and a enol tautomerizes to give you a compound. So here also it is the same scenario. You have a hydrogen abstraction, so cleavage happens here. It's a radical cation. So this bond cleaves homolytically, right? One electron goes here, one electron comes here, another electron comes here. So what this electron combines, you get an olefin, and then you have the enol undergoes tautomerization to give you the compound. So this is a radical cation and this is a neutral molecule. So all two bond cleavage processes results in from a radical cation resulting a radical cation. And here is another example, okay, 1, 2 substituted compounds, 1, 3, 1, 4 disubstituted compounds. If you form a radical cation of this under EIMS scenario, what you get is the loss of the stable molecule which is HX, X could be OH or halide or whatever, or amine for example. You could get the final thermodynamically stable product as a neutral molecule, and the remaining part undergoes, here is a radical, here is a radical, this combines and forms this molecule with a radical cation. So all these involve 2 bond cleavage process. Here also this bond and this bond is cleaved, right? And all the 2 bond cleavage processes, you start from a radical cation, you generate another radical cation along with a stable neutral molecule. Okay, that is the story. So this neutral molecules could be of various types that is shown here. It could be ethylene, it could be ethylene, or it could be acetylene, or it could be carbon monoxide or whatever. Right? So all of this could be possible. Again, McLafferty. So McLafferty can have varieties. It can have various varieties. Please keep in mind, in the initial slide we talked about only the carbonyl system, but that C instead of double bond O, that O could be carbon also, right? This X could be carbon, this X could be nitrogen, this X could be oxygen we saw in the previous slide. This double bond could be part of a benzene ring, okay? That C double bond C could be C triple bond C also. It could be an alkyne also. So in all these cases, you will have the McLafferty coming provided you have the gamma hydrogen present in the molecule. If either side of this functionality you have 2 gamma hydrogens, either side of this functionality, which means this side, here also gamma hydrogen is there, this chain also is long enough and you have a gamma hydrogen, then you must expect double McLafferty rearrangement. Okay. So mass spectrometry, you will find all these possibilities and you should look for that in the mass spectrum. These are very signatory signals which you will easily be able to figure out, and that is most probably the dominant signal that you will see in the mass spectrum. Moment if that is a McLafferty pathway you are noticing in the mass spectrum, that will dominate over the rest of the alpha cleavage pathway that we saw previously. Okay. So the route wise, so fragmentation pattern is quite signatory when such functional groups are present in the molecule. So what are the mass losses that you see in the mass spectrum? Typically one is lost, then it is a hydrogen atom loss. If there is a mass difference from m dot plus peak from the molecular ion, if you are seeing a peak at a lower m by z with a mass difference between them is 15, then you can say methyl is lost. If m minus 26 is lost, then you can say it is an acetylene. If it is 28 is lost, then it could be loss of ethylene or it could be carbon monoxide. How do you differentiate if it is carbon monoxide or ethylene? You should use a high resolution mass to identify if there is a carbon monoxide or ethylene. If it is m minus 29, then it could be ethyl CH2 dot CH3. CH3 CH2 dot is what is lost in the cleavage process. If it is m plus minus 31, then it is a methoxy loss. So it is a list of fragment ions that you should keep in mind. Moment you look at the mass spectrum, you know the molecular ion peak and you see the lower masses, and then look at the difference, what could have fragmented from the molecular ion is what you will be able to figure out easily. So the highest mass loss is the loss of iodine, which is m minus 127. Okay. And if there is a mass loss of 79 and 81, like we saw in the case of benzyl bromide, you can easily figure out. And for the benzyl cation, there will be no isotope peaks. Right? To start with, you had isotope peaks because bromine was there. Once bromine is dissociated as Br dot or chlorine is dissociated at Cl dot, then there will be no isotope peak for the fragment ions. That means you can easily find out, okay, the mass difference of 79 or 81 is lost, or 35 or 37 is lost from it. So this you will be able to find out.
Swayam Prabha, Digital India, Educated India.